Okay, for this podcast, we're talking about density. So we can continue to use what we've learned about factor label when we use that for density problems. So here's a picture of a density column, which is, I think it's pretty cool looking, and it demonstrates one of the concepts of density, which is if I have two substances with different densities, that one will float on the other. So the most dense is going to be down at the bottom here with the bolt or the honey. And the least dense is going to be up here where the lamp oil or the ping pong ball is. And it doesn't matter whether it's a liquid or a solid. You can separate them. Well, you're going to have liquid layers for the solids to sit on. But that's a general idea with density. So high density down here and low density up here. Okay, so density is defined as the object's mass divided by its volume. So density is mass over volume. So if I think about the density of aluminum, which is reported as 2.71 grams per centimeters cubed, you can look that up in your textbook. It's listed on your packet on page 21. You can look it up online. So it's widely reported. And so what does that mean? Well, that means if I look at this cube down here, and let's say this cube is 1 centimeter by 1 centimeter by 1 centimeter, making it 1 centimeter cubed, then I can say for every 1 centimeter cubed of aluminum, there are 2.71 grams. So that's what it means. If I make the volume the same, then I can compare the density of substances. So here's a cube, 1 centimeter by 1 centimeter by 1 centimeter of aluminum, and for every one of these, it weighs 2.71 grams. Okay. So we use the formula density is mass over volume, but I can also solve that equation to solve for mass, which I often have to do in problems, or to solve for volume. So let's see how we would do that. So if density is mass over volume, and I want to solve for mass, I need to isolate mass, and I can do that by multiplying both sides by volume. I cancel out the volumes on the right, and I end up with mass is volume times density. It's a little more complicated for doing volume. You need two steps. So if density is mass over volume, I do the same thing I did for the mass, and I end up with mass is volume times density. Now I have to get volume isolated, and to do that, I'm going to divide both sides by density. And when I do that, the densities cancel on the left, and I end up with volume is mass over density. Now you can memorize this, or you can use your algebra skills to figure it out when you need it. Okay. So I'm going to come back to the top statement here about when density can change and talk more about the density being an intensive property. So density of solids has a specific volume, and liquids. Density is an intensive property, which means it doesn't change. So remember, it's a characteristic of the material. So it doesn't matter whether I have these ball bearings that are aluminum, or this wheel that is aluminum, or this irregular shaped object. If they are pure density, they will all have exactly the same density. Okay, because we're talking about how much it weighs per every unit, same size unit of volume. Okay, so this might weigh the most, but it's also got more volume to go with it. So the common units we use for density are grams per milliliter or grams per centimeter cubed, and those are the ones we use most commonly. However, when we're talking about gases, we often talk about grams per liter, and I'll look at why in a second. And sometimes, not usually, you'll run into pounds per inch cubed. Okay. So this is a repeat of the other slide with a different diagram on the bottom. So in some cases, density can change with temperature. So if you look at the diagram on the bottom, your solid is pretty close together, and so are your liquid particles. But you imagine if I heated up a gas and it was open so that the particles could leave, that the density could change quite a bit with the temperature. As I heated it up, the molecules are going to spread apart. Okay, more so than a solid or a liquid. You can change densities of a liquid slightly, but most of the temperature change that affects density is going to be with gases. Okay, so you can also imagine for a liquid or a solid, you're going to have a lot more mass for every unit of volume compared to a gas, which is why gas density is often represented as grams per liter. Okay, grams per liter, because you have a lot less of it. Okay, so let's take a look. Here we have a table of some common densities, and let's take a look at what we have here. So if I look at these really low values, hydrogen and oxygen, that's because it's a gas, right? So a lot less particles in the same amount of space are going to mean a much lower density, because these are all the same units of grams per centimeter cubed, which would be the same as grams per milliliter. So how many grams for every milliliter, how many grams for every centimeter cubed. Okay. Here we have some liquids, and liquids are usually about 1 gram per milliliter. Now you need to know that density of water, now here listed as 0.998, but remember it as 1 gram per milliliter. Okay, that's one of the things you should know, you should memorize, because we'll use it all the time. So, and then there's a variety of solids. You know, a lot of solids are going to have a density around 1 or 2 or 3 grams per centimeter cube, but some of these heavy metals are going to have much higher densities. Okay, so let's take a look at problem A. Problem A says a liquid solution has a mass of 28 grams and a volume of 32.5 milliliters. What is its density? And would this solution float or sink in water? Okay, so let's take a look. Whoops, I went a little too fast on that. Okay. Alright, so we're identifying the things that we're given and what we're trying to find. So we have the mass, we have the volume, and we're trying to find density, and we're also trying to answer the question of whether it will float or sink. So density is mass over volume. So if I take 28 grams and divide it by 32.5 milliliters, I get a value, and I need to make sure my sig figs are good, right? So I've got 3 sig figs in my mass, 3 sig figs in my volume, so I want 3 sig figs in my answer. And my units are going to be these, grams over milliliters. I get them right from the units in the problem. Okay, so the answer to the other question is, would this solution float or sink? If water is 1 gram per milliliter, this is less dense, so this is going to float. Okay. All right, problem B. An irregular piece of lead has a volume of 15.7 centimeters cubed. What is the mass of the piece of metal? Okay, so we are given the volume, trying to find the mass, but we also are given the density in the table up above. Okay, so you can look that up, and it's 11.3 grams per centimeter cubed. So the density of lead is 11.3 grams per centimeter cubed. I use my formula, rearrange it for solving for mass, and I get volume times density. And when I plug in my numbers, 15.7 centimeters cubed is my volume, times my density, which is 11.3 grams over centimeters cubed. My centimeters cubed will cancel out, and I will end up with units of grams. My calculator says 177.41, but I have to look at the number of sig figs in my givens, which was 3 for the volume. I'm not constrained by the density, right, because that's a conversion factor. So I want 3 sig figs in my answer, which would be 177 grams. Okay, in problem C, we need 147 grams of grain alcohol for an experiment. Will this fit in your 100 milliliter beaker? So, a little hint in the parentheses said find its volume. Okay, so we have its mass, we're trying to find its volume. Grain alcohol we can find in the table, find its density. So we're going to rearrange the equation. First, the density is mass over volume, multiply volume times both sides cancel on the right, and we end up with volume times density is mass. But now we have to arrange this to solve for volume. So I'm going to divide both sides by density, and when I do that, density cancels on the left, and I end up with volume is mass over density. Okay, so now I can plug in my numbers. So volume is 147 grams over my density, 0.789 grams per centimeter cubed. Okay, so let's plug in the numbers, and when I do that, I want 3 sig figs, because that's what I have in my mass, in my given. And let's talk about units. So I have grams on the top, and grams over centimeter cubed on the bottom. So the first thing I can do is cancel out the grams and the grams. Now that leaves me with no units on the top, and basically 1 over centimeter cubed on the bottom. So if I have 1, whoops, that went way too fast. If I have 1 over x, when I bring this up, I flip it, right? And I end up with x. So that's a relationship in doing problems that you need to understand, right? So I end up with units of centimeters cubed with 3 sig figs. Okay. So in the lab we're going to be doing some work with density, and we can determine density of an object by measuring its mass and measuring its volume. But sometimes, and that's not so hard to do if I have, let's say, a cube of metal, and I can measure its length, width, and height, get its volume, and then I can put it on the balance and get its mass. But if I have an irregular shaped object, like this rock, then I need to use the displacement in water method. And what I do is put the rock into a known volume of water, see how much the water goes up, and that amount the water goes up is my volume. Okay? And then I just divide the two. Okay, we're going to stop right there.